everyone. Thank you for the reports that you have sent to me. I received it so far, I think more than 10 reports, but I'm not so happy from what I have seen in these reports, because some people may do a procedure which is different than what we have taken here. I got the point that we need to review, but I will do that at the end part of this lecture. We will review together, maybe from step 0, in general, how we proceed in these projects. But let me just start today to show you how you can achieve a tuning for the last exercise or homework. I don't hear so much about the results that you are going to provide in your report. However, I want to see that you know the procedures. You know how to get the match. You know which parameters should you use to tune your property. And I think all the guidelines are already provided in your guideline papers. So just let me open the last project. Okay, so you know the lecture before the last one, we reached the point where we took the data at saturation pressure. So we have, and that was step number 1. So we have PSAT. When I say data on PSAT, I mean we have to match PSAT and oil density at PSAT at this pressure. So this is step 1. In step 2, we try to match or to keep this matched and try to match CCE. So when we say PSAT, it means saturation pressure plus oil density at this pressure. This is step 1. Step 2, we match CCE. We mean by CCE relative volume. And I have seen that some people try to calculate the average absolute error for compressibility. Okay, that was required in CCE guideline, but we don't apply the rule that we have to have average absolute error below 1% here for oil compressibility. We just try to, because we try actually we match relative volume, not oil compressibility. Then the oil compressibility will calculate it from here and should be improved. However, we should only evaluate this one here, relative volume. So this was step 2. step 3 seemed not very easy, at least for those who already achieved the task. So in step 3, I hope that I will write that way. So step 3. Step 3, we try to match DLE, but at the same time we have to keep this matched and this matched. This is the way how we go from step 1 to 2 to 3, and the last step will be step 4, which we will maybe talk about next week. So today we will not take a new step. We have to, I've seen that some of you are not able to at least follow the guidelines in the training manual. So I think it's not useful for us to go further. We have to review, we have to make sure that everyone understands this. So we are here in this step. When I say data at saturation pressure, I mean saturation pressure and oil density at saturation pressure. Both those have to be matched with the average absolute error less than 1%. I'm not sure at least for. Okay, I'm not sure about this percentage. Let's keep that. But I know that for BSAT, it's okay to be off by plus or minus 50 psi. This is the range. For example, we have our bubble point is 2620 psi. If you try to tune DLE, then your saturation pressure changes to a value with plus or minus more than 50%, then you have to improve this. For example, I have seen that some people try to match, then they got this value with more than 2,800. This is not acceptable. You totally shift your bubble point pressure. So it's not acceptable to have this value because it's more than the real value by 200. So this one is not acceptable. You may have good results here, but you should always keep in mind the results here. So we are in this step, and in this step, we have seen that in CCE we match relative volume. In PSAT we match two things: PSAT and oil density at saturation pressure. Here we match several things. We start by RSD. When we say D, it's for differential test. It's not the GRS which we use in our calculation. This value needs to be fixed. So we also have beta O, and this is also differential. It's also it needs also to be fixed. So and we match oil density and oil, let's say like this, oil viscosity. And the most important step here, you exclude this one here, So again, I will repeat. Last week we have homework, which in this homework we try to match DLE with keeping CCE and BSAT data matched. When I say CCE data, it means relative volume. When I say BSAT data, it means the bubble point pressure and the oil density at this pressure. So we already matched those in step 1 and step 2. So now we want to match DLE. But the problem when we try to match DLE, those ones can get worse. So the question now, what I should do to match this data without destroying those two here. In DLE, we have RS, D, and this is for differential. And you will, next week, we will have another training. Then you will learn how to fix those values to have the real RS and the real beta O, which are used in our reservoir calculations. So the task here, we want to match those without destroying those. Why we need to match those? We said that for DLE, you have acceptable error, which is less than 5%. Without doing anything, we found that here we have more than 5%. So there's a question here. For this one, I don't remember. Was it okay or not? Okay. Yeah. Let's just this one. So let's put across here. So this one was okay. What about this one? I think it was okay. What about this one? Okay. So before you try to do the tuning, you have to evaluate your equation of state. Why you do the tuning without evaluation? If you evaluate, if you just go to tuning without evaluation, then you will not know which parameter you are going to match. You just like in a dark room where you try to do something without knowing what you have to do. So don't go to tuning before you evaluate. That's why in the training, the first step was to evaluate those values. Please, if anyone has a question, you can ask. Interrupt me in any point. And if you feel that I have to repeat something, you just ask me to do that. I think it's not useful to go further without understanding what we are doing now in this step.
For evaluating phase, should we calculate it with all the lab data in the weighting factor default, or we have to set them into as reference?
Okay, you are talking about weighting factors.
Yeah.
We will talk about that after next step. Just hold on and wait for that. I will say why we have weighting and why we change them from default values.
So for evaluating, we do not use default weighting factor.
The problem that the default weighting factors are all the same. So you don't focus on certain property more than others in your regression process. Just be patient. I will come to that one. Here, when we evaluated our data, we found that we have only a problem. So do you understand the procedure that we went through? step 1, step 2 at least. Did you understand this? Step 1 and step 2. I need yes. Did you understand this? Step 1 and 2. Or I will repeat them. Yeah.
You said that for pH saturation, saturation pressure, we need to have the kind of amount that is not more or less than 50 psi. Okay, so when do we see this change in the step 3? We might see this change that it is, for example, instead of having 2,600, it is 2,800.
Okay.
You're not going to see it in step 2 because we have.
Yeah, I will. Yeah, in this, you see this bottom here, Vsat. Here you just enter the temperature, which should be constant, because we are talking about Vsat at constant pressure. I have seen that some people they change this temperature. This cannot be right because we want to know the oil density exactly with constant temperature, and the equation of state should have constant temperature to know that. So here we choose the number of points, and we just press calc. This is the calculated values by equation of state. Here oil density and here Vsat. Again, the question: have you understood step 1 and 2? Before question, have you understood this? I will repeat for the last time. I don't think that's very difficult. So, step 1. Maybe even before this. Okay. We have oil and gases. So you know oil, gas. This is simple. When we deal with gas or we try to simulate gas, we have this equation PV equal to which called this equation is able to find the relation between PVT, which is the name of this first. So this equation is able to find any relation. If you, for example, if I have P and T, then I can find the volume. So this is the idea. Why we need to know the volume? It's important to determine the properties of our gas, either downhole or in the surface. So this equation is really important for us. But what about oils? The case here is different. They extended this equation, which was obtained from real gases, to oils through van der Waals equation. So he just changed this equation to another form. He said P it's not clear. So this equation was extended to include liquids, but they found that this equation is not able to describe liquids, so they extended that through van der Waals equation. What van der Waals did? So just he said Uh, the problem was in this equation was with this factor z. I need to calculate z by charts, and it will be very complicated to include those correlations in this equation. So they found, okay, we want to ignore this one, and we will try to have this parameter here and this one here. So we don't have any more z factor, and also the n, which is here. So this term here and this term, both of them describing the force or the interaction between gas particles. So actually this equation is still for gases. They solved the problem for Z, but they found also this equation is not able to describe liquids. So that's why they needed to extend that again to include liquids by Peng-Robinson equation, which I don't prefer to write it again here. It's nearly the same here, but more complicated. So this equation, Peng-Robinson, it's okay with oils. And there is also improvement with this equation, which is called volume shift. Why volume shift? Just let me. So I need to at least this part. This is all already mentioned in your manual. Don't worry about it. So we know that any fluid will behave like this at constant temperature. We talk about pressure and volume. So we know that any liquid or fluids will behave like this, even if you increase the temperature, you will have the same shape here. We have seen that this part is gas and this part is oil. So if we are talking about this part from here to here, we can describe this by dV equal to ZnRT, this part, or by Van der Waals equation, or any equation of state. All equations of state are able to describe this part because they were actually generated from this equation. We already have this equation, which is our reference here, and can describe this part. And what we have done, we improved this equation to have this without z factor, or to have this which is able to describe also gas plus oil. Peng-Robinson. So this part, we always can simulate that part. It's not complicated. I mean, this part for gas. The problem that this equation, let's give this equation green color. This equation will always go like this. So after this point, it will not be able to follow this part. For Peng-Robinson, let's say for this part here, and I will, okay, remember, we will continue with red color here, with this one. This one is going maybe to do something like this. Let's ignore this one. Let's make it more simple. Okay. Let's talk to the last step. We say our biggest improvement in this equation that we could extend it to Peng-Robinson, which can describe the gas with oil. So let's say Peng-Robinson is described by a red color. Yeah, it will. So you remember that the problem with real gas equation, it will not describe this part and this part. It will just goes up. In Peng-Robinson, it will describe this part. Here it will have something like this and like this. So it will describe this point here, but it's not straight line here in this part. But that's already solved here. Because we already know this equation is a cubic equation. When we solve it in terms of finding volumes, we will have 3 volumes. So in your calculations, you don't worry about this because we can differentiate between this point and this point. Here the slope is minus, and here is minus, and here is positive. So here positive slope, minus, and positive. So we ignore this point because we already know that this reading is just a wrong one. We have only one problem in this equation, which is this one here. The equation usually is not able to describe the volume for liquid. You remember, this is oil. This is liquid. So this is the problem. What's the solution for that? It's just found that we accept all the results for this equation, Peng-Robinson, with just one fixing way. We said, okay, we have this point and the real point is here. So we have this difference. Okay? So let's say this volume, from where we take this volume, which is from the red line. From where? This is from Peng-Robinson equation of state. So we call this volume, which we obtained at this point, volume from equation of state. How about this one? This is measured in lab. So we know this is our true volume. V star. What we have to do now, we say, okay, anytime we calculate volume with equation of state, then I will minus this value, which is C, to have this volume. So what actually will do is just to shift this curve from this point, from here to here. So we will have like this exactly. When we do this fixing, we just will say, okay, the volume will be equation of state volume minus C to have the real volume. which is correct. So we have this, which is wrong and needs to be fixed with this correction factor to have the real volume. This correction factor is called volume shift. So now, by volume shift, from its name, volume shift, we have equation of state, we calculate this, while in reality we have this. So we shift the volume from here to here by just a value C, which will bring the equation of state values exactly identical to the real volume. So that's why, in general, you have to remember this. When you deal with oils, liquids, you need to fix this part. If I have a gas reservoir, then I don't care about this because I am always in gas phase. So when we deal, and that can be shown here. So we have two-phase diagram. So this is the critical point. If our reservoir temperature higher than the critical point for the fluid we have in the reservoir, then we have gas. If we are below the critical temperature, then we have oil. So we only can evaluate our reservoir phase according to critical temperature. So if we have a critical temperature which is measured in the fluid. I cannot take fluid sample, then I measure the critical temperature. So I know the critical temperature for that fluid, but now I want to ask, what's the reservoir temperature? Let's say we are here in this point. This is the temperature for the reservoir. Then the temperature for the reservoir is higher than the critical temperature. Then we have a gas. If our reservoir temperature is here, then we have oil in the reservoir condition. The temperature in the reservoir is always constant. So in the reservoir, we will have something like this. The pressure will be reduced due to production. So after a while, we will go from P1 to P2 due to production. The pressure, we will lose pressure. So in this stage, we only in this part. You are able to describe the properties of your gas by either PVT and PV equal to Z in RT. You are able to describe this by that equation. But the problem of this equation, you need to find Z at each pressure stage. Let's say you are going here by each 100 psi. You need to find Z1, Z2, Z3, Z4, Z5, let's say Z6, this is P6. So describe the gas properties at each stage. You need to calculate Z factor at each stage. And that can be not useful in terms of reservoir simulation. You will not say to your reservoir model, please wait me, I will calculate Z factor and then I will come back to you. So that's why they improved this equation. They improved this equation, van der Waals or Peng-Robinson, just to be able to describe the gas properties in different pressure stages without needing Z factor. So we know now exactly what we can do in this part. Now the question, uh, in this part, do we need to use, or the first question, can we use Peng-Robinson in this part, which is here? Can we use Peng-Robinson equation? Yes. Because we already we say that Peng-Robinson will describe this part, will go like this, and then will come like this. So this part can be described by Peng-Robinson, but can be described by van der Waals, can be described by real gas equations. So this, we don't have a problem. Now the second question, in this part, do we need volume shift? We don't need, because we are talking about gases. Also for gases, we will not measure, for example, the bubble point pressure, because this point will be the saturation pressure. From here, this point is bubble point pressure, and this point is dew point pressure. So, if we deal with gases, there is no need to use volume shift. It will do nothing for you, and you will not need that. So, this case is only related to liquids. And it's better when you do PVT modeling. When you don't need something, don't use it. Don't use that thing. So, if we are talking about gases, we say this part can be described by Peng-Robinson, van der Waals, or this equation. In PVT modeling, you will not find real gas equations because it will not be used there. They use it just in exercises now to show the students that we have PV equal to Z in RT. It was created, I don't know, 500 years ago, and so just to show you. But now we use those equations. So when we in the software, you will have two choices, either Peng-Robinson or summarizing one equation. So I have mentioned just Peng-Robinson, but both of them are able to describe gases and liquids. But Peng-Robinson is more reliable in terms of liquids. It's forced. It's okay. We know that both of them are derived from PV equal to Z in RT. So actually, those equations came from gas equation, not liquid equation. But they extended this equation to be able to describe liquids. However, Peng-Robinson is forced more than the Ridley-Wong equation to be able to simulate liquid part, this part. So both of them are able to describe this part. However, Peng-Robinson is more reliable on this part because it's forced more. And now the question: if you deal with gas condensate, or let's say our volatile oil, in these fluids, okay, we have seen that Peng-Robinson can provide good results, but Ridley-Wong is more reliable in terms of that this equation is not forced too much to be able to describe this part, which is liquid part. So, okay, Peng-Robinson is better, but Ridley also have some advantages, and that's why we have the choice between both of them. In your case, if you don't understand which one is better for me, try both. Try both of them. I have seen many studies where they have this doubt. So they say, okay, we will start by Peng-Robinson. I will have that model. I will tune that model. and I will see how my matching is. Is it good or not? And then they repeat the same procedure with survival. Then they compare. Then from average absolute error, I will know which one is better. Again, if we are talking about liquid, about this part here. So this here will go like this in separator, and this is dry gas. This is just an example. If we deal with oils, then we are talking about this part here. Then here we cannot use either van der Waals or PV equal to Z nRT. Now we are talking about liquid phase, and liquid phase is this part here. So instead of coming from here in the gas phase, you are starting from here now. From the higher pressure, then you go like this. So this part is exactly this part here. So from here to here, we are above bubble point pressure. And that's why we describe this part here by CCE. So this part is described by CCE. And this one here by CCE. This point here is the bubble point, which you see here. It's the same. So what's the first step in our guidelines or training? Why we do this software? We just use this equation, Peng-Robinson, which is able to produce this behavior, and from that equation we will compare from here, starting from here. I will compare this part, or starting from this point exactly. I will compare this point, then this part, and then I will go to this, either in separator or DLE. So actually DLE will describe, okay. In DLE we will describe this part here, which is below the bubble point, but at constant temperature. And here we will describe this separator. And we use separator this, and it's actually starting from this point, from the bubble point pressure, to describe this part here. So both tests, they go from saturation pressure until very low pressure. This is for DLE, for example. It goes until here, but we don't know, maybe we use until this point, because we measure oil properties at constant temperature. So it means that, like, our measurement is in this line. This is DLE. In separator test, we start from saturation pressure, but we change the temperature and the pressure that we will have in the surface. Because as you know, the oil will come from the reservoir, come to separator. And this separator may be two stages. So this is stage 1 and this is stage 2. So what we will do, just we take oil sample at saturation pressure, then we go to this condition and to this condition. And we will see that next week. So now at least I want you to remember that the fluid, the oil in the reservoir, we are at constant temperature. That's why in lab, our measurements are at a constant temperature. So this is what DLE will going to describe to us. However, my reservoir condition can go, for example, until this point, and from this point to the separator, we will have different curve. But just understand this. In DLE, we start from saturation pressure, we do our measurement until a very low pressure. So this is DLE measurement. And all of that at constant T, which is, again, reservoir temperature, in case of oil. So this, when we were talking here, we were talking about different reservoirs. They are not the same. This is gas reservoir and this is oil reservoir. So, so you understand now why we have CCE, why we have DLE. If we imagine that we have a reservoir, this is a reservoir, and we have a well here. You know that this is, we can call it R, or drainage radius, the extension of your reservoir. So this extension of your reservoir, you will have the higher pressure here, and the pressure will go lower to here, to BWF. To have a flow, will reduce the pressure at this point to produce your oil or gas. So from your initial pressure until BWF, your bubble point may be below BWF. So in case of your bubble point, or let's say saturation pressure.
Could you please repeat this part? I couldn't listen.
Yeah, okay, I will repeat. Okay. We say that, imagine that you have a reservoir. Far away from your well, you will have the highest pressure, or we can call it reservoir, average reservoir pressure. So here you have the highest pressure. Firstly, your situation is like this. The pressure is equal every day. So there is no reduction in your pressure. It's all the same. So imagine that your pressure reading is here. So this is your initial pressure, and this is your bottom hole flowing pressure. So when I drill a well here, I start to produce. So I need to lower my bottom hole flowing pressure, to lower the bottom hole pressure to have a flow. So that's why we lower the pressure at this point in the well. Then the hydrocarbons will flow, and I can produce. So I don't know if others can see that. So just imagine that you have a reservoir. Far away from your well, you will have an average pressure. In your well, you can control the bottom hole pressure. That pressure, if you reduce, you will reduce. So to what extent I can reduce this bottom hole flowing pressure, it depends on how much should I produce. So the more is the delta B, the more is your rate. So imagine that you are, even if you reduce your bottom hole pressure until a certain value, you are still above bubble point. So this reservoir, all of it will be above your saturation pressure. So we will have only one phase. All the reservoir is above the saturation pressure. Why we have two phases? We will have only one phase. So this phase can be oil or gas, because I have saturation pressure. If in case of oil, bottom hole flowing pressure is more than the bubble point pressure. So I have only oil phase, and so on with gas, dew point pressure. So imagine that we are still here, even with when we reduce the bottom hole flowing pressure, we are still above the bubble point pressure. If we reduce BWF, we are still above the bubble point pressure. Then we are still here in this part. Then all the oil properties here can be described by CCE. We don't even need DLE, because we are above the bubble point pressure. Is that clear? So that's why we have CCE. However, at certain point, we will need to reduce the bottom hole flowing pressure more. Then we might be below the bubble point pressure. And then that's why we have DLE. Then, for example, let's say at this point here, you have your bubble point. You need to divide the reservoir. In this part, you will use CCE, and in this part, you will describe the oil properties by DLE. So, because we are here above the bubble point pressure, that's why we use this part. So, now I will talk about the steps that we have done in our training lecture. We start by this point. We say, okay, this is our step 1. This is step 1, which is exactly here. You remember, in the first project, what have we done? Saturation pressure. So we match this point. We try to match this point. If we are talking about liquids, then to match this point, it's better to use volume shift. So that's why in the first project, we use volume shift. Volume shift, but in the saturation pressure project, we have to match two properties: saturation pressure and oil density at saturation pressure. And we have seen that when we use volume shift, the oil density at saturation pressure is fixed. You know that the oil density is calculated by this equation: mass over volume. And without volume shift, this volume will be equation of state volume, which is wrong. But when I use volume shift, then they fix this value. Then they will use this one here, which then will fix this volume, and you will have the right value for oil density. You know now why we use volume shift. And we have seen, or we have said before, you need volume shift to fix oil density. If you fix oil density, for example, let's say you don't use volume shift. You say in the software here, volume shift. Okay, you say volume shift, no. Okay, I will not use volume shift. Then I will not have this fiction, but you will try to match this point. You will match You will try to match the oil density at saturation pressure. Then will need to match this part or this point here, but you will have a big shift here. You try to match the point with the wrong procedure. Yeah.
So I think we start to making we start with this one, with this option.
Well, if you deal with oil, this is your first step. If you deal with oil, this is your first step. To fix this problem, you know that you understand that your equation of state is not able to produce exactly the liquid part. So that's why you will, before you do tuning or anything, you will have to use volume shift.
That means if we do not use the volume shift as yes, it will calculate the matching with the volume of the equation of the state, which is wrong.
Yeah, I will view that here. So just you know that your fluid will behave like this. So you know that the van der Waals or Peng-Robinson equation is able to produce this part, but with a percentage of error. However, this is the real shape of that equation. It will be able to describe this part. So this part is okay, and this part is not okay. What you have to do here, if you don't use volume shift, and your first step is to match this point, you want the equation of state to match this point. This is your equation of state, the black one. And the red one is the real behavior. So now imagine that you are going to shift all of this to match this point. So now you will have like this. You will match this. Okay. But you will destroy this part here. So just you reverse it, everything. It was wrong here and okay here. Now you match it this to make it okay, but here it's wrong again. You shift everything. That's why this is wrong solution. This is very wrong. This equation, which is without volume shift, it's called the two-parameter equation, because we use only omega A and omega B for these calculations. We need third parameter. That's why we have a cubic equation of state. Cubic equation of state will include volume shift. So now, using two-parameter equation of state to match your data at saturation pressure, we said this is the first step. So you are trying to match the data here at this point with a two-parameter equation of state, then you will destroy everything. You will be able to produce this part, but you will have a wrong calculation here. And as you know, GR, it depends on gas. And then you have the wrong values here, and then you have errors everywhere. So what's the solution for this? We have seen that, okay, we we know that the real behavior is like this. So now we know, and the equation of state is able to produce this part. So it's okay here, and it's wrong here. Now we say, okay, we don't change this part. We accept this part. We leave it as it is. And what about the wrong part? We say it's okay. We know that we have to measure this point in lab. So this is how we call it. Okay, V star. It's measured inside lab. This is the real value which I should get. And this is the equation of state volume. So we have to shift this to this one. So it's easy. Just measure this difference, and whenever you have our liquid volume, then by this equation, the equation of state minus the constant that is the difference. It means like I accept this part, I accept everything except this part, I will shift it to this direction. So I will only shift this part, then we will have also here, okay. We will able to produce liquid part and gas part. And that's why in this point we say for liquids we say yes. For volume shift, because our first project to match the saturation pressure, which is this point, and the oil density at this pressure. And oil density, if we want to match it, then we need volume shift. Then we will have the right volume. Then when we calculate density, M over V, we will have the right volume. Then we will have the right oil density. So this is our first step in our project. This is step 1. This is step 1. Step 1 is exactly this point. We are talking about only one point. We are not talking about stages. Only one point. So this point, what we can calculate from equation of state at this point, we can have the pressure and volume. The pressure, okay, we can calculate the pressure, and the volume we fix that value, and then we try to match our equation of state to have those values. So remember, at the first project, at the first one, we start like this. We say volume shift, yes. We say Peng-Robinson because it's the most reliable equation of state, especially with liquids. And our data was for oil, for liquid. So this is the first choice. Then we enter the saturation pressure data. At BSAT, we enter two things. The saturation pressure, which is the bubble point pressure, and the oil density at this pressure. And we have said that you have to take care about units. Just enter the right value here with the right unit. So here, at this point, the bubble point pressure is exactly this one here. Is exactly this one here. This is the first step. Density, it's calculated. The density here is calculated from the value that the volume that you got from here, and you know the mass, and then you will calculate density. So this is our first step. Yeah.
When we use forward shift to correct the slope, and then how can we know that the right side, the gas side, is correct or not? Because we don't have any saturation data viewpoint that
Here in volume shift, your equation of state is always able to describe the, without changing anything, it's able to describe this part. So if you deal with gases, you will see that when you apply van der Waals equation or Peng-Robinson, you will see that this part is always described correctly by default. So at initial state, we always able to describe this part. And here we don't match this point by shifting everything. We say only this part. We shift only this part. So we have not changed this part. We already know this. However, in step 2 and 3 and 4 even, we will evaluate gas-oil ratio and gas-oil ratio. From gas-oil ratio, we will know the volume of gas versus or over the volume of liquid. Gas-oil ratio. Gas to liquid ratio. I mean oil by liquid. So when we came to that point, we will see, are we able to, because beta O or RS, it's always about volumes. Even in lab, we measure always volumes. We just convert them to ratio. So we always deal with the values here, the volumes. For example, CCE, we measure the volume. Then we divide the volume at each step over the volume at saturation pressure. And also in DLE, we measure the volume of gas and liquid. Then we divide them to have RS. And so on for separate. It's always in lab, you may always use the cell just to change the pressure and to measure the volume. And you know how much fluid you have inside the cell. We always measure volumes. In lab, you always got volumes, and then you change them to GOR or beta O or beta G and so on. So we will know that in our further steps. So we know the first project, we enter the real value, which is the bubble point pressure, and the real oil density, and try to shift this one here to have exactly the lab data. So this is my reference data, and I will try to match both of them by volume shift. And for saturation pressure, you can use two ways. You can either match the saturation pressure by binary interactive coefficients or by TC/PC eccentric factor. Of course, for the pseudo-components. Why pseudo-components? We already discussed this before. Pseudo-components measurement or measurements inside lab is not reliable. They are not pure components to know. For example, if methane, we know only we have methane, then we know the critical properties for this gas. But for pseudo-components, they are only, mixtures for hydrocarbons. So we don't have a specific measurement for these components. So that's why we change the properties to match this data. So step 1 is to match this part. We have seen together when we matched saturation pressure, if you remember, and I hope that you remember. When you match when you finish it, the step 1 and you go to step 2, which is the evaluation of this part here, this part, which is step 2. Which is CCE. This part is CCE. This part here is CCE. When we match this point and we went through step 2, which is CCE, what was the error percentage? Was it acceptable or unacceptable? CCE, have we done tuning in this step or not? No. Why? Because when we shift all of this here, it was already above this. We shift only this point, but we know when we shift this point, we will have matching all this part here. And now you have, you should understand why we don't have to do tuning here in this part, in step 2. We match only one point here. But that means if you match this point, then you will shift all the curve here. Then you will match all the data here. Then in step 2, you will not need tuning. So that's why when we go further to this step, we just entered the saturation pressures, stations, and the relative volume. And then we used the equation of state to calculate CCE. We go to CCE, which is this one here, and we say calc, then we say plot, okay. Yeah, when we show the calculated values, which is indicated here by the red line, with the measured values, which are indicated by green, we found that we were able exactly to discount this part. Remember, here the temperature is constant. This is the reservoir temperature. So we are moving like this. So the pressure, remember, the pressure, okay, this is the initial reservoir pressure. Then the pressure decreases and the volume, the relative volume will increase. So this is exactly this part. And you have seen that we were already able to describe exactly the lab measure, which is the green pointers, because we have seen that the equation of state initially was like this. But when and this is the real data, the red one. This is the real data. So when we shift this curve to here by volume shift to match only the saturation pressure and the oil density at this point, then all the curves come to the right position. So that's why when we do step 1, step 2, we will not mainly, or in most cases, we don't need match. We will find that we already matched this part.
But is it after the changing average absolute error? Because at first it was 20%, and you said the slope is okay. Then we changed it, and on Excel we plot another diagram, and we changed it. It was like below 1%.
It was already below 1%, as far as I remember. It was around 1%. It was not more than 1.5%. And you can see that even in your project.
So it is always like that.
Yeah, in most cases. When you deal with oils, so then you are talking about this part. Then when you match this point with volume shift, this is the most important point. With volume shift, then you will shift this curve to here. Then when you come to step 2, you will find that your CCE data is already matched. Is that clear? Okay, finally. So now, do you think it's okay to go to step 3? Step 3. I need vote or something like this. Yeah.
But in CCE, we also calculate compressibility.
Yeah.
When we compute compressibility, we cannot get a good or appropriate error.
Yeah. Okay. That's
So we have to tuning again.
that's good question. Compressibility is calculated from where? From relative volume. And relative volume is already matched. So we cannot improve the compressibility. We just care about this part. We match relative volume. Because we calculate compressibility from relative volume. So we cannot match compressibility with, I mean, how we can match compressibility? We only match relative volume. Because compressibility will be calculated from relative volume. And in lab, we know that compressibility can be measured between 2 points. However, we use equations to describe this compressibility. And as far as you have in this part here, in this part, as far as you have average absolute error less than 1% for relative volume from CCE, then that's your duty is done. For oil compressibility to have error about 10%, that's acceptable due to the limitation from the equation or due to the lab measurement. Because you have another choice. If you try it, maybe you will surely get good results, not 11%. Instead of taking the measurement for compressibility, just, okay, I want to calculate the compressibility from this point to this point. So now we have 2 points, either for the equation of state and the lab measurement. So we can use the compressibility equation to describe the compressibility for oil using the equation of state values and using the measured values. And then the results will be comparable with each other. You will find a low percentage of error in this case. So, in my opinion, that part which we compare compensation should not include it anymore in the training, because maybe some students confuse it when they say this percentage of error. So just pay attention to this one here. At CCE, you will try to have average absolute error below 1% for oil for relative volume. So now we will go to step 3. In step 3, we are talking about this part here. So we will try to match this part. In lab, we have beta O, and we have RS, and oil density and oil viscosity. So this part, we will have, you know that there is a percentage of liquid and gases here. You know this? This is two-phase region. So you have in this part, and above you have 100% liquid, and this is 100% gas, and between them you have equality lines, and equality line is describing how much oil and gas I have. For example, here, for example, in this equality line, the first one, I have 80% liquid and 20% gas, for example. But here, I have 80% gas and 20% liquid. And usually they say, okay, liquid is 20%. And liquid here is 0% for this line. It means 100% gas. So in DLE, we have a percentage. And that percentage can be described by RS. because in DLE we measure RS, and RS is volume of gas versus volume of oil. We take gas and oil at that volume, and then we will bring them to the standard condition. However, if you don't understand this, just understand it's the gas over liquid ratio. So that's why we try to match RS with beta O, which describes how the oil will expand or how the oil will shrink when we lose gas. So even this volume, we will have beta O, which is like this, beta O, volume of oil over volume of oil. But this is at, which one at reservoir condition and which one at standard condition? Yeah. So, is it reversible? I was depending on you. Is it okay or no?
Should be.
I don't have a problem. I can reverse it again. So, here we describe what's the percentage or how much oil will be shrink compared to the oil at the condition before going to the standard condition. So, for example, imagine that your oil volume like this, and then you go to the surface and your oil volume will be like this, will be double. Then your beta O would be this volume, which is at reservoir condition, and your at standard condition you will have this volume. Actually, this one, in case of you, in case that you don't lose gas, liquid will expand. But in real case, at reservoir condition, you have this oil, but when you go to the surface, you will have this volume, because you lose gas, and your liquid volume will reduce. So when you divide this volume by a small value, then you will have this number reducing until it goes to 1. I mean, in standard condition, you will have the same volume ratio. So in DLE, we describe how much gas and oil are together and what's the change in the oil volume. What's the change by beta O, or formation volume factor. So when we match DLE data, we will exactly try to simulate the reservoir measurement or the PVT measurement. So this is step 3. In step 3, so you understood step 1. We match B sub data. Step 2, CCE, and we found it's already matched. In step 3, we match DLE. But remember, at each step you try to keep the previous one matched. So now, our duty is to match DLE with those ones matched. So if I match this with destroying those, then I lost everything. Okay. The first, if we show that in the software, okay, we know here that when we compare the lab measurement with the calculated data, it was okay. Then we go to differential. In differential, we have several pressure stages with gas oil ratio, beta O, oil density, oil viscosity. And we have seen that this part is described by RS and beta O, which are here. So by matching these data, I am able to describe the two-phase region. That's why the DLE experiment is always below, starting from the saturation pressure, because we want to describe this part here. So we entered the lab data, and I will say why we have weights here. So let's just avoid that now. And then we came here, differential. And when we show the GRS versus pressure, we found that we have the lab data is here and the calculated data is here. So we have error percentage here. When evaluated this percentage, we found we have error more than 5%. Let's go back to what we have entered in lab. For differential, we are talking about RS, D, beta O, D, we are talking about 4 properties that are measured in lab. So this is already provided in your lab data, in your PVT data. We have RS, beta O, oil density, oil viscosity. Those are measured in lab. You will use the equation of state to produce those values, and then you will compare them together, as we have done before with CCE and saturation pressure. Now, before I start tuning, before I do anything, I need to evaluate. Is this data, or can we simulate this data by equation of state? To know that, you just go to differential, calculate, and you can show plots. So your equation of state is not able to produce this one. It's not able to produce like your PVT measured data. But from this, we cannot know the average absolute error. How much the error from here to here. That's why we use Excel sheet. We take these values, and from them we can calculate average absolute error. Do you need to see that again, or I just show you the values which were obtained? Maybe I do it just for gas oil ratio. So this is gas oil ratio from equation of state. And I have already prepared Excel sheet. Here I have lab data, so I know this is exactly the measured data. And here I will enter the data from the equation of state. So I just come here, press paste, and then I will find that I have 14% error, which is not acceptable. I will repeat that with other properties. When we compare oil formation volume factor Okay. So now, after just in the third step, at this step, we found that now we evaluated all of them. So the percentage here is 14. Here is 1. So what do you think after your evaluation now? Is all of this acceptable or not? Where's my problem here? So we have a question here. For here it's okay. For here it's okay. For here, okay. Small okay. It means it needs to be improved. We will try to improve that. So we have a small concern here. We cannot say okay. So, but in our procedure, this one we deal with this one in a special way. So this is special. Oil viscosity is special. What is special about oil viscosity? Oil viscosity is matched alone. Keep it like this. At the end. So just exclude this from your mind. Forget about it. You deal now with this, this, and this. Okay. I forget about this one. So, what's the problem here? I have a problem only in this part. And we have seen last week that if we try to match this one, we will destroy this and this. And the problem is not easy and complicated. I have seen so far that maybe no one could achieve acceptable match. And in your term project, you will deal with more difficult data, and you are required to get the match. At least you will try to have, if you could not have less than 5%, at least just be around that number. Don't come with error which is 30%. Try to be near to 5%. If you could achieve that number, it means that you are able to deal with your equation of state. You are able what you have to do to fix those properties. And I will show you today how to get the match. You have to consider several points. I have mentioned them before in last lecture, but no one have wrote them or mentioned them. I will try to mention that those rules again. Then we will see, are we able to achieve the match or not?
Sometimes when I was matching the data, for example, for the Z factor, as I was going through the software, it was not giving me some of the steps of the Z factor. For example, looking through Reservoir, the first one is not given, and the last one. And as I went through it, even more than that, were not given.
Sometimes you maybe will not be able to see RS or beta.
Yeah, exactly.
Yeah. It means in this case your equation of state is like twisted. So it will give wrong results and cannot even provide some results. So maybe it does not see that you have a liquid also even here in this condition. So you have to you are trying to calculate RS while you are dealing with gas, for example. So you will not have this value. This is what happened to your equation of state.
First it was okay, but
yeah, when you tune your equation of state, or you're forcing your equation of state to match a part, then you are totally lost on the liquid part, for example, or vice versa.
what does it mean?
You need to match. You don't need to make a severe change in your equation of state. Try to match it a little bit with fewer parameters. The more parameters you will use, the more complicated it will be for you. And we have seen that. Maybe everyone was thinking that if I use all my parameters with the idea to match everything at the first step, then I will finish my homework and that's it. It's not that easy, especially in your term project. So, so we have a problem now here with RS. For this and this, we already know that the error here is acceptable. However, I can repeat that for PSAT, if we just, as we did here, we use the equation of state to calculate the differential liberation. We do the same with saturation pressure. So, at this temperature, so this is the pressure, which is calculated by the equation of state. So we have exactly the same number, and this is the density. So we have matched the data at saturation pressure. And there is something good here. When you match the oil density at saturation pressure, you will find that the oil density at DLE is already matched. And it means when you match the density at this point by fixing the volume, then that volume will help you even to describe the oil density at DLE. So you will know that when you mismatch your equation of state, or when you have a high error percentage in oil density at DLE, you will have also a high percentage error in oil density at saturation pressure. It's like they are linked to each other. So, and don't forget, the oil density at saturation pressure is exactly at the same point in the DLE here. So here it's the saturation pressure, and here is the oil density. This is measured inside lab. So you see, inside lab, this point, this is measured inside lab, and this is inside lab. So they are near to each other. They are exactly the same. So this point is the same here. And you will have a nice conclusion from this. When you match, I have said this before in the last week. I've said the most important properties to match, even in DLE or in DLE, let's say, are those. The first line here at saturation pressure. You know that if you match this, you will have a correct number here. But what about those two? When we compare those two with those two, there is, for example, at least here for RS, and you compare those. Here it's 854, and here it's 963. So now the question, I have two rules. They are the most important rules for you to get the match. The first one will be choose the fewest points. The fewest. It means I have from here to here, I have, for example, 10 points. Do I need to match all of them? And we have said that the most important one is this one here. What about trying to match only this point and we exclude all of this? And we know that, and I remember that I draw RS here and I talked about this point. The properties, for example, now you understand this, I will remove it from you. So, when we have, imagine that we are talking about RS. So, in DLE, RS will be, so from here it's not measured but it's constant. So here it's your bubble point. So now your equation of state is something like this. Why you try to match all the points? While if you match only this point, which is the most important one, you will have other points matched. So exclude, don't just ignore all this curve. Deal with this as one point. And this is the rule. Take the fewest points for your matching. And this means that try to match RS only at this point, at saturation pressure. We know that if we match this point, the curve will be shifted to this here. And then we will never, for example, it's impossible to have a curve like this. If we match this point, we will never have something like this.
But actually, the difference shouldn't be always the same by matching.
Yeah. When we match this point, then because the function it will already have the same shape. So that's why when we match only this point, you know why we are not able to have the matching when we're trying to match the all points? Because in CCE you have one point, even if you give that point a high weight, and I will mention why we have weights. So here we deal with one point, here we deal with several points, and here we deal with several points. So it means like it's not fair. We are trying to match 40 points here with trying to keep this matching, which is only one point. This is not fair. We are forcing our data to match something where we are not able to keep that something, which is different thing. So what we need, it's like you are dealing with complicated problem where you have to catch it with different areas or different sides. So, okay, I will catch you from here and from here and from here to here, then I have the right shape. This is the way. So, this is the first rule. This is, you can call it the golden rule. It will help you so much. And the second rule, I forget. So, actually, one moment. Yeah, the second rule, I don't remember. Just use as few parameters as possible. It's the same way. Okay, here I use this point, for example, and this point, only the first one. Then, if we change a lot of parameters, also this is a question. What's the difference between parameters and properties? You have to pay attention to this. When we say properties, it means RS, beta O, oil density, oil viscosity, or saturation pressure, anything you measure in lab. Those are the properties. That's why we say liquid properties. What's the properties of my liquid? It means oil density, RS, beta O, and so on. But what's parameters? Are they different? Yes. Parameters are not exactly the same as probabilities. Parameters are the ones who I use for the tuning. So when I do tuning, when I go to regress, this is the parameters, which you see here. TC, PC, assembly factor, volume shift, binary effective coefficient. Those are the parameters. Why you call, and variables, you can call them. Why we call them with this name? Because those are the parameters of my equation of state. And when I change them, I will use them to match the PVT properties, which are the beta O, GOR, and so on. So this is the difference. And this can help you in writing your report. I don't understand if you say to me, okay, I will match the lab parameters with changing the property of eccentric factor, for example. You will reverse everything to me, and then I will not understand. If you say parameters, then you are referring to those. If you say properties, then you refer to relative volume, saturation pressure, and so on. So the second rule, use the fewest my laptop hates me, I know that. So you have pseudo-components. The second rule says use as few as possible in a small range. So that's why when we edit the range here, we go to regression and we exclude close and we change the range here. And the range here should be 1.1 and 0.9 here. Don't worry, I will go back to this. I have to mention only, now I have to talk about weights. Okay, we know that when it's impossible to do this by manual tuning. To do this by manual tuning, it's impossible. You will try to get the match with keeping that problem in your mind, then you might get crazy. So just don't, the only option you have, auto regression or auto match. In auto regression, you will try to match everything at the same step. So that's why we have weights. And I will show now what's weights. What are weights and why we need them. Imagine that at each step, okay, we have RS for differential liberation test, which is measured. And we have we always to do matching, we need measured data and equation of state. So we compare between them. And then we have average absolute error. So we have a number here, which is reference number. And here we have another number. Okay. They are different. So we have another number. When we compare them, we will have a percentage of error. Let's say this percentage is 5. Okay. This will happen also with beta O. So this is by equation of state, and this is measuring, and I will have a number here and number here. And here I can have several points. So I can have from 1 to 10 or 20. And here I can have 20, I don't know the same number, 10 values. So we always compare them. Those values are different at different stages. So where I put the weight and why I use them. The idea of weight is easy. Okay, let's say that here I have also 5%, and so on with other properties, with any number of points that I have. So here I have 10 points, here 10 points, here I have 1 point, and here I have maybe 20 points. So the weight idea will say the following: I have this error of this error percentage. Then I will use a number. When I multiply that number, I will make this error higher. It means I increase the percentage of error. Then, from that number, I will force the equation of state to match that property more than others. How can that be done? It's like this. If I give, for example, 2 to this weight 2, weight fact, then the error percentage is 10 here. Here I have 1 weighting fact, then the percentage error is still the same, it's 5. Then the software will say, okay, I have higher percentage of error here, while here it's 5. So I have to pay attention more on this. So that's why I give higher weight for this property than this one. The weight is just to increase the average absolute error for that property. So at the end, I will have the lowest error here. Then the software will say, okay, this is acceptable to me. And I will force my equation of state to reduce this to 5%. And then when we come back to the original one here, we will divide it by 2, then it will be reduce it to 2.5. It's like a loop. You got lost or... So again,
you're reading to use a kind of weight factor, for example, for PVT, we have to use 5 or...
Yeah, now I'm talking about the weighting factors which are already used in PVT.
For regression, you're not supposed to change the weight. First, you set a kind of weight, and that's it. We fix it.
Yeah.
For the next step, you're not supposed to change the weight. That's it.
Let's say, okay, here, either from here, where we enter our lab data, or we can go back to this window from here. It's the same. So here, we have this weighting. This is where we give weight. And I said 2, it's exactly the number which I have shown here. I said, when we say to this property here, okay, take this, for example, let's say this one with 2. And we say set weighting, then this property will have 2. And this one will have 1. So the software will take 5%, which we imagine that you have 5% here. So 5 multiplied by 2, then you will have 10. Then due to that weight, the software will see that you have a higher error here in this part. However, here with beta O, we have weight 1, then the software will see that 5%. Then I have to focus more here. And the way of regression, it will try to reduce the average absolute error, and the highest error is here. So that's why we do iteration. We change the properties to match this data. Then it will see this 5%. You are seeing this as 5%. but the software seeing this as 10%. Due to the higher weight that you already choose here. So the software will try to improve this to 5%. Then you will be happy, okay, now I have 2 and 5%. Is that clear? Yeah.
So we choose weighting according to our CCE. We find the absolute error in DL and CCE. Then we use the DL.
Each property, you will give it a weight. That weight depends on several things. Now you just understand that you have weights. From where you get weights, I will come to that point. So you understood that when you give weights, higher weight will mean higher percentage of error. Then the software will focus more on this property to improve it. Then you will see that it's improved. So those are the weights. How I should deal with weights? In PVT textbooks, when you see reading Whitson or Ali Dan's book or anyone, go to the equation of state tuning part. Go to that part. Tuning, how they do tuning. They will recommend you with weights. They say usually the highest weights are the highest weight will be given to the saturation pressure. So in this software, we will come to this one. I give it the highest weight. However, the default in the software is the highest weight for all of them. Then the software, if all of them having the same weight, it's not matter if all of them having 1 or 10. It will change nothing because all of them having the same weight. So I will multiply this by 2 and then multiply this by 2, and then I will go back to the same number with all properties. So weights are not working or do not work in a case that all your properties having the same weight. They are useless. You don't differentiate, the software will not differentiate between them. All of them having the same weight, then your weighting is not does not mean anything to the software. This is the first one. There's also another point. When you have only one property, for example, we have said that the oil viscosity is matched alone. Then if this oil viscosity matched alone, giving the same weight to the all points which are here, it's meaningless. You give a weight for this oil viscosity while you are matching this alone by itself. There is no other properties that you need to match with. However, that will be useful only in one case, if you give different weights to those points, or if you exclude points. What does it mean to exclude points? Okay, I will say to the software, there's different cases. You can take this point with certain weight. You can say to the software, try to match this point with that weight, and this point with different weight, and don't match anything else. So in this part, we will exclude it from our tuning. How we do that? Through those buttons, include, exclude. So I hope that now you are able to understand what's weights. Weights are given from PVT textbooks. So this is the question: from where I can have weights? It's recommended. However, you can use them according to your fluid. For example, I found that the highest error is here. Why I don't give higher weight here? to say to the software, okay, focus more in this rather than this and this. And this is second golden rule, which I forget before. So try to use different weights with where you have a problem. I have seen that, I don't know, I've seen that in some case, when I use lower weight here, I improve this. Don't ask me why. Even me, I don't know why. I have lower weight here, then I improve this value. What you can try, just, okay, start, you have a reference value. You have a reference values. We say that usually we give low weights for these values. So start by these low values. These values starting from 1, they can either be 1 or 2 or 3. You have 3 options. So if you started by 2, okay, I have, for example, 2 here in this point. I started with 2. Then I found that I could not achieve the match. You can still try 1 or 3. And maybe 1, which is this way, can improve your results. I have seen this. I don't know why, but I have seen that.
So you have to just be in the range of 1 to 3.
Yeah.
Supposed to change it.
If 4 will improve your results, use it. Even if you think 10 will help you to achieve the match, use it. But that will not. You will go out from the recommendation. Then you will expect to make the process more complicated. They deal with these problems in PVT textbooks. For example, Whitson, he already dealt with several fluid samples, and he found that the acceptable range is from 1 to 3. So when you want to change that, however, if you change it that and you got better results, then that's okay. Everyone ways to do this. Yeah.
So are you saying that for each parameter we can make different weighting factor for the same property?
Yeah. For example, here I can get okay. Which one is the most important one? The properties at this script. So I have 2 options, or actually 3 options. Either I give all of them the same way, or I say this is the option 1, which we have tried last week, or we tried last week. So the second option would be, okay, I know that this property is the most important one. Why I don't give the highest weight here and lower weight here? How I do that? I just select this one. I say I can give 3 to this. So this is. So when you click this, this is 3. Just see, when I select this, this is 3. When I select this one 2. So why I don't give lower weight? So I select all of them, and I say, okay, 2 set. So not all of them. Just by this way you can get different weights. So then you set the software will focus more here rather than here. The second, remember we have said that you have 3 choices. The second one to give all of them the same way. The first one to give all of them the same way. The second one to give different weights. And the highest weight will be for the most important one. The third choice will be to, okay, I know that this is the most important. Why I have to match all of this? I will exclude it from my matching. This is how I exclude. I select all of them, I press exclude. Then the software, when you do regression, you will not see these points. The software will only try to match this. And this can be very helpful to match the other points and to keep the data from other steps matched. The main problem. Yeah.
But at the end of the day, we have to match all of them. So if the first one is matched, we can go through into the other ones.
When you compare them, will you see that in your Excel sheet? When you calculate average absolute error. When you calculate average absolute error, right, you are calculating them for all the points. And we want to make sure. And but now, if I match this, do you think those ones will be improved or get worse? This is the idea. I've drawn the figure here and said, if you match the point at saturation pressure, then you will improve other measurements. So this is the step. And now I don't know what I have. So. So remember, now I will start again from this point. And I hope that the students who have not delivered the homework yet, they should try the same procedure. At least now you see how you can solve this. So try to have a low error. So now we have this problem. We want to match this, between this and this, and we say this, we will lift that at the end, and we will try to keep the saturation pressure matched and the oil density matched. So, yeah, I will try. So, I don't know, but I have tried this thing. I know that in my case, maybe I have tried that before, so I know what I have to do, what I have to use, what I have to do with my equation set. For you, it was difficult because you don't know how you deal exactly with your equation of state. Which points are the most important? Maybe this thing was not clear for you. To me, I know that, okay, I have to give the highest weight for the saturation pressure. So I keep that with 10. And oil density with 5. We already agreed on this. So, and this is 1 point, 1 point. So we have 2 points. Now we have 2 points. In step 2, we talked about relative volume with this weight. And in relative volume, we have seen that if we match oil density by volume share, this one maybe is not needed. I mean, let's just show that here. Okay, this is your lab data. Starting now, I will give the suitable weights and the suitable choices for me. So in saturation pressure, I have 2 points. So I will take both of them with the suitable weight. So 10 here and 5 here. For this one CCE, do I need to take all the points? And I know that if I match the density here by volume shift, then the relative volume will be already fixed. So the suitable way of thinking is to say, you have two choices. You either take only the first one, or the one which is at the, sorry, the one at the PSAT pressure. Okay, not one, not this one. This one, the first one. Yeah, I forgot. You have two choices. Either you take the first one, or you exclude all these points. In my opinion, it's better to exclude them. So, in this procedure, just forget about this. So, okay, I will not try to match CCE in my regression. If I want to match only one point, I can use include and exclude. So, let's go to differential. We say, okay, take the RS at saturation pressure with this weight, 3, with the highest weight, because we have the highest error here. So we took the highest weight with acceptable range. I mean with acceptable value of weighting factor. It's as recommended in our references. So, and for beta O, we will give the point at saturation pressure with low weight. So we know it's already matched. We will take the point at saturation pressure with lower weight. How to do that in the software? Just take the first one. Okay. I will copy that. So I will give 3 here and 1 here, and I will exclude all of this. I already excluded the other points. And why we do this? It's not fair. It's not fair to the software to try to keep PSAT matched, which is 1 point for the saturation pressure, with this, which is 10 points. So they will give the same weight for those points or for this point. Actually, you are saying that the highest weight is here, and the number of points is here, making the highest weight is not here. And maybe is not here, maybe is here. So the number of points will affect your tuning. It's not the same if you have 1 point or 10 points. They are different, even in terms of weights. If you have 10 points with 1 person or 1 weight, that means for that property 10 weight. It can mean 10. It can mean 10. 10, I mean weighting. So the number of points will increase the weighting. Actually, this is what actually do. The number of points will increase weighting. So let's say, okay, I will exclude all of those. Also, those points maybe they are not important for your tuning. They will try the process complicated, and the golden rule says take the fewest number of points. So this is the rule. I think only this one, which is the most important one. Here, I also do the same. But here I have a question. Do I need to include this in my tuning? I said take the fewest number of points. Do I need to include this?
No.
What? When? This is the point. We know that if we match the oil density at saturation pressure, this one will be already matched. So why we try to do that again? It's just you make your problem more complicated. So this is the way. I take this, I will take this, I will not see to this, and I will not see to the relative volume, because I know by oil density matching, actually by oil density matching at saturation pressure, I improve two things together. I improve CCE and I improve this one here. So that's why I exclude them, this and this. So now we will try. So this is the procedure. It says, okay, take the RS at saturation pressure with this weight, take this with this weight, and exclude all other data from CCE or DLE. So how we do that? Okay. Now we go to regress. And then, okay, for saturation, we will take it. For density at saturation pressure, we will take it with medium. So this one here, we have the choice. Either we include it or not. We will see now. We say that if we match this one here, it will improve this one. So that's why we ignore this. So no, we have not checked this choice.
Why did we check the first one? You said that it is already there.
Now we will try to match the DLE with keeping those matches. So don't forget, you have to keep those. So I will ignore this. I will. What about oil density at differential liberation? We don't want. What about this? I have changed the weights here. Low, low. So, and here we take the only the first point or the most important point. So you can see that here again. This is the point and this is the point. So just you see that we take the first point and this the gray color here, it means that we excluded all the points here. However, we tried 3 now. You might try 2 and you find that your results improve, or 1. So you can decrease this. And this one, we already give 1. You can try 2 and 3. And then I need these comments in your report. I don't want someone who, okay, I have this percentage of error and that's it. Yeah, you need to think, okay, what does this mean to you? I have to pay attention on this. Do I need to take all the points here and some logic thinking? Even if you could not achieve this is what I have, I said last week. I will ignore having the right average absolute error, but I need people who do the same which we do here. I need a procedure that is already recommended in the lecture. I have seen a report with trying to match the viscosity at the first step. It's not okay to start with this point. It will make the process more complicated. So I think the lecture is finished. I will just show how this can achieve. Okay, I will need to. So I will need to uncheck those, and remember here we use 1.1. Yeah. So now, one moment. I will need this because this will improve the saturation pressure. You remember that the saturation pressure is matched by this. However, you can match also the saturation pressure by these parameters. So it's better for you to include this in tuning and do that for the last pseudo-component. For example, like this. All pseudo-components with the same value, and And we need volume shift to fix the density, oil density. And the first step always to try use all of them. Here I said that use the lowest parameters as you can. You may start by using only those. The second choice, use all of them. The last or all of them. Remember this. The last or all of them. So now I will just press regression, and you will see that the process is faster because we have only few pointers and we have already no error. And we will see that now. You can wait that in new home. So I will just cancel, okay? So here the result. For P saturation, it's okay, still near 6 psi high. So this is okay. This one is okay, not very high. This one is okay, we will see. And this one is at least near. We will calculate now the average absolute error for those. Oh. You see now, we were able to achieve a value lower than 5% for RS. Let's see the other things. Oil formation volume factor. Oh. Yeah. So you see that we could achieve this. We could achieve this. We could achieve this. For oil viscosity, we say that we will list it at the end. So now, if we show the other properties, what happened to PSAT properties? You see that you are acceptable here, you are acceptable here, you are acceptable here and here and here. So, and in CCE, you are also acceptable. You can try that and down. So now you achieved this, you only have this. So this is your last step. Now you will try to save that model. You say, okay, this is acceptable matching. Then I will copy this and I say oil viscosity. And now in this model, I will try to match the oil viscosity. And it's good here. You are lucky to have, when you choose this one, the software will uncheck all these choices. In other softwares, you will not have this option. So they are following the rules here. So now you will have to match this. But when I match this, it doesn't matter weight, don't forget. Weights is not matter. Make you know it's not matter. You use the same weight for all points, and you use only this property. So when you choose this, and maybe you use this model here. Okay, shift. Then okay, this is the Differential. So yeah, with this model, we are not able to achieve matching. Maybe we use the same this one, and you see that you use critical volume. Maybe this model also is not useful. Yeah, this model is okay. When I use Peterson model, I reduce the error to 15. So when I press cancel, okay, I'm not sure, but I will see. Oil viscosity. So you still need to improve that. However, try different models. Improve this value to lower than 5. Then re-enter the other boxes again. Do they still in the acceptable range or they will change? So you need to keep this less than 5% with those. So maybe I will give another chance. So you need to try this at home to see what's the problem, how I can improve this. So now you still have the problem with only viscosity, and I think it's not very hard. You just try different models with different choices, and maybe you got the match. Okay, that's good. It's not very hard for the viscosity to deal with alone, but you have to keep those matched. And that's it. Maybe if I match this, they will change. Then I will repeat again. So you will be in a loop until you match this without destroying this and this. And now it's easy because you deal with 1 point here, 1 point here, and 2 points here. So it's easy. It's not very complicated here. So to go back to here, it's easy. So don't worry about this. Now we take only 1 point here, 1 point here. And that's it. Today I don't want to keep everyone here for more than 15 minutes. However, I will stay for answering questions.